This video is going to review some basic rules for differentiation from section 3.3. So in section 3.1 we introduced the derivative as a definition involving the limits, and here we're going to learn some of the shortcuts that allow us to find derivatives quickly and easily rather than going through the long definition. So let's start off with a couple of those rules, and I'll write them out in general and then I'll give you some examples. And as I'm writing, you'll note the paint on my hands. Please disregard that, and hopefully it doesn't bother you too much there, but I was doing some painting this weekend and I was not able to get a lot of it off. So anyway, I just thought I'd share that with you. So here are some basic rules for differentiation or finding the derivative. So first of all, we have the constant rule. And hopefully remember that the constant is a real number that is typically multiplied by a term. But in this case, a constant can just be a single value as well. So in general, if we want to take the derivative of some constant c, we're always going to get 0 as an answer. So the derivative of a constant is always going to be 0. And again, c is some real number. Okay, so the derivative of any number is always going to be 0. That's our first rule. Our second rule is the power rule. And this rule is extremely popular. We will use this a ton. If we're going to be taking the derivative of some x to the n power, so anything raised to a power, an x squared, x cubed, any power at all. Patterns have shown, and someone discovered way long ago, that you can find the derivative quickly here by taking the power n and multiplying it out in front by x, and then reducing the power by 1. So n times x raised to the n minus 1. Alright, so that is our power rule. Okay, next rule is the constant multiple rule. And essentially what this does is allows us to take any function and multiply it by a constant c. So here I want to take the derivative of some function f of x multiplied by some constant c. And what the rule tells us is that it's perfectly fine to keep the constant off to the side here for a minute, find the derivative of the function f using whatever rule you may need to use, and then just multiply that c back in. So in other words, take the derivative of the function and multiply the answer by the constant. Alright, the next rule is the sum rule. And this rule should seem fairly obvious, but what it says is if you're trying to take the derivative of two different terms that are added together, and I'm going to clarify that and say that subtraction is fine too. So we're trying to take the derivative of some f function and some g function that are either added or subtracted. Well, the sum rule says that it's perfectly fine to separate them and to go ahead and find the derivative of f. Whoops. Let's get rid of that prime for now. So we're going to take the derivative of the derivative of f, and we're going to take the derivative of g, and we're going to take those two derivatives separate, and we're going to either add or subtract them. So in the end, we have the derivative of f plus or minus the derivative of g. So in other words, if you wanted to take the derivative of two different terms, you would do the obvious, which is just take the derivatives separately and then add or subtract those together. Alright, e to the x e to the x has a very special derivative. The derivative of e to the x is always itself. Okay? So there are a lot of things that we can do to look at why this occurs, and most of those have to do with graphs and limits. But it has been proven, and it is shown a little bit more detail in the textbook why this is true. But you'll always want to remember that the derivative of e to the x is always itself. It's the only function where that happens. It's unique in that way, and it's something that we'll always have to remember. All right, so those are our basic rules. Now let's try using some of those rules in some examples. Okay, so I'm just going to write down several examples here. And the first example, we've got f of x equals 3. The second example, this function g is going to equal x to the 5th. My third example is a function called h, 2x to the 6th. I've got a couple more here. The next function, which I called f, is going to be the function x cubed plus 2x plus 1. And my last function is going to be the function g of x equals 3 e to the x plus 5x squared plus 4. So why don't we pause for a moment and use some of the rules that we described above to find these derivatives, and we'll come back and take a look at the answers. Okay, hopefully you paused the video in order to try some of these examples. Now let's take a look at their answers. So for number 1, we had a function that was constant, f of x equals 3, and we took its derivative, and the derivative of a constant is always 0. So the answer to that one should just be 0. Number 2, we had to use the power rule. So we take the exponent 5 and we multiply it out in front, and then we decrease the power by 1. So 5x to the 4th is the derivative. In number 3, we had the constant multiple rule and the power rule. So we had this constant multiple of 2. So I set it aside for a moment, and then I used the power rule to find the derivative of x to the 6th. And then I just multiplied the 2 times the 6 to simplify and make it 12x to the 5th. The fourth one here, we had several terms. So we had to use the power rule, and we also had to use the sum rule, where we were finding the derivative of different components that were all added together. So just find the derivative of each piece, and then add those results. The derivative of x cubed is 3x squared. The derivative of 2x is 2. And the derivative of 1 is 0 since it's a constant. And finally, we have here the derivative of an e to the x. We also have a constant multiple out in front. So take the derivative as usual, and the derivative of e to the x is always itself, and then multiply by that constant multiple 3. The next term asks us to use the power rule, 10x, and then the last term is a constant, so its derivative is 0. Alright, so those are some basic examples of how to find derivatives using some of these shortcuts or some of these rules. Let's go ahead and look at second and third derivatives. Okay, so we should be able to find the derivative of different functions multiple times. And so we call these higher order derivatives. Higher order derivatives. Okay, so a second derivative would be denoted by f double prime of x, f double prime. And you find that by taking the derivative of your original function f, and then taking the derivative of that again. So we're doing the derivative of the derivative. giving us the second derivative. And of course, we can do that again and again and again, and the next iteration would give us the third derivative, denoted by f triple prime of x. And here we would take the derivative, and we would take the derivative of that function again, and then we would take the derivative again. So if we take the derivative of the second derivative, we get the third derivative. Now I'm not going to do any more of these, but I just wanted you to know that after we start to get up higher than 3, you might see notation that looks like this. F to the fourth of x, meaning the fourth derivative. It happens rarely, but you might see it. All right, let's take a look at a couple of examples of finding higher order derivatives. So let's say we have a function f of x that equals 3x to the third minus 5x plus 12. Let's find the first derivative. And remember, the point of these shortcuts is to be able to do it quickly. So let's do a power rule, a constant multiple rule, a sum rule, as well as a constant rule. We basically have everything wrapped up into this one example. So its first derivative is going to be 3 times 3, which is 9x squared, minus 5, and then the derivative here is 0. So our first derivative is 9x squared minus 5. The second derivative would be 18x, and the third derivative, if we needed it, would be 18. Alright, so in order to find higher order derivatives, we just start with the first derivative and we continue to take the derivative from there. Alright, a couple of things that we need to talk about from here. The next item on our list here, on my list anyway, is to be able to write the equation of a tangent line. So equations of tangent lines. Now, this has been a theme since we began our course. We know that the tangent line represents the first derivative, or the slope of the tangent line represents the first derivative. And so we often are asked to not only find the slope of that tangent line, but to also write the entire equation of that tangent line. So remember, to write the equation of a line, we typically use the formula from algebra, which looks like this. And it's called the point slope formula, y minus y1 equals m times x minus x1. So we need the slope, and specifically the slope of the tangent line. And we can use our derivative rules to quickly find the derivative of a function and evaluate it at a specific x value in order to get the slope of the tangent line at that point. Speaking of point, that's also something that we need to know. And we find that point by taking our given a value and evaluating that with our original function to get the y value. So let's put this all together with an example. And let's let f of x equal e to the x. And our given a value is going to be the natural log of 3. Okay, so I chose this example because of the e. So I'd like you to go ahead and find the derivative, evaluate that derivative at the given a value, figure out the point by getting the y value, and then put it all together to write the equation of a tangent line. We'll pause and we'll show the answer. Let's finish this example off by taking a look at the derivative of the function, which would be e to the x, evaluate it at natural log of 3, and hopefully you remember the property here that the e and the natural log cancel out, giving us a slope of 3. The point's x value is natural log of 3,